First of all, remember that this is your derivative function. And they're asking us where our function is increasing. What do we know about the derivative when your function is increasing? Your derivative is positive, or the derivative is greater than 0 if your function is increasing, yes? So if this is the derivative of the function, where is it greater than 0?
It's always above 0. I don't know.
So here's what I don't want you to do. If they give you the derivative, don't tell me it's increasing from here to here because it's going up, right? Because that would be if it's the original function, you can just see where it's increasing. I just want to know where it's bigger than 0. Do you agree that that's going to be where it's above the x-axis? So this whole part of the graph is above the x-axis, or could we say between -2 and 2 is above the x-axis, or positive y values? So we could say that it's increasing from -2 to 2. It does come down and touch 0, doesn't it?
No, maybe I think it's sitting right above 0.
No. Like it comes down. It just doesn't go below 0, right? Like it touches 0 and comes back up.
So it could be greater than or equal to 0.
Oh, I see what you're saying, right? All right.
That's why I said it should just not touch 0.
I'm okay with that. -2 to 0 and 0 to 2. You want to say that? I'm with you on that.
Do you have to put the U?
You can. Remember, you could include or not include that, and so that's why it kind of would be okay either way, whether you included 0 or not on that. But I like that answer better. So using the idea that knowing that increasing is where your derivative is greater than 0, that means decreasing, we know, is where your derivative is less than 0. So if they give you the derivative function and you want to know where it's less than 0, do you agree that that's the same as saying where is it below the x-axis? Which would be this part and this part. Or could I say that it's decreasing from -infinity up to 2 and from 2 to infinity? And then, so this is part A, this is part B. Part C says estimate the x-coordinates of all local extreme values. Are my local extreme values here and here? Because this is the derivative, right? Right? You have to think about this is not the original function. If this was the original function, you would just look for high and low values. But this is the derivative, so you have to think about where on the derivative does my graph change from increasing to decreasing?
Are you looking for the bowl? Is that what this is?
No,
What is that?
that's concavity. Do you agree that before -2 we would say that this is negative because it's decreasing there? And then after -2 it becomes positive, so it changes from increasing to decreasing to increasing? So at -2, is that where it changes? And then if I come over here, what about at 0? Is 0 going to be a max or min? On the left of 0, what are my derivatives? Are they positive or are they negative?
I'm just thinking about it like, it seems like all of that first part should be increasing, and then that should be decreasing and increasing. You know what I mean?
If this was f of x, you're exactly right. If this was the original function, you would say it's increasing where it looks like it's going up. And then it turns and it's decreasing, and then it's increasing, and then it's decreasing, right? That's if it's the original function. but this is the derivative. So they're graphing the slope values. So you have to really think about when they give you the derivative, what that means for your graph. And when they give you the derivative, where it's positive means increasing, where it's negative means decreasing. Because this is where the derivative is positive, this is where the derivative is negative. Everything on top is positive. So that means all the y values is what I'm looking for. Do you agree all these y values are positive? Right, zero's not going to be one. Do you agree that if I was making an xy chart for this, x would still be my x values, but y kind of represents your slope values? Agree with me on that? That's kind of what you want to think about. So when you pick numbers up here, they're all positive y values, which means all your slope is positive. So Ethan says 0 is not going to be a max or min, because do you agree that it's positive on both sides, so it's not changing? So 0 is not a max or min. But what about 2? 2, it's positive above it, because it's positive above the x-axis and negative below it. And we could even go as far as saying whether negative 2 and positive 2 are max or mins. Because on this one, do you agree that it was decreasing and then it changed to increasing? So I could even say that at x equals negative 2, that is a local minimum. And then at 2, it changes from increasing to decreasing. So at x equals 2, it's a local maximum. And do you remember back, I don't even remember when at this point, but do you remember when we were looking at graphing derivatives and the zeros always were the max and the mins, because those were your turning points when you would try to match the graph of the derivative with the function? And that's still true. The zeros can be your max and mins. They're not always max and mins, but they could be your max and mins. So make sure on your homework today you pay attention to what they give you. If this was the original function, we would do this totally different. We would just look to see where it's increasing and look to see where it's decreasing and give those same intervals. Okay? A whole bunch of AP questions. We're going to look at some of these next week. Like I went through and picked out some sample AP questions where they like to give you graphs and they like to ask you questions about max and mins. And sometimes they give you the original function, and a lot of times they give you the graph of the derivative. So like my number one thing when we start reviewing for the AP test is step 1, figure out which graph you're looking at. Are you looking at the original function or the derivative? Because every time they give you choices when people mix them up. So let's make sure that we figure that out. I think that was my last example, right? So maybe let's take a few more notes today, and then we'll wrap it all up on Monday. So we're gonna call this day 2.5. We finished up yesterday's, and I don't know that we're gonna get through all this today, but I want to.
Homework tonight is going to be leftovers from yesterday.
And maybe a couple from today. I know. It'll be fun when I create it.
Unless you make Nathan or Kimberly or I grade it.
Make me create it. Unless I just give herself a plus.
I deserved that. I earned it. I
Nathan
got
gives
it.
himself A pluses all the time.
Nathan gives himself your number 1 stickers every time. And then he gives everyone else blue smiley faces.
Or bugs. I think today we're just going to look at the second derivative test, and then on Monday we'll wrap it all up of learning what functions give us some derivatives. And I just have this whole list of things of if you know this, then this means this. If you know that, then this means that. And it's just a big long list that I'm going to make you write out, but we'll wait till Monday.
Do you have to remember all of those things?
Yes.
I don't like to always pay attention.
Why is that thing on his head? I like that he's wearing the pie hat.
It's a pie hat. Look.
It's like pie.
Have you
It
worn it
says-
on your head before? No, it's, I mean, for a moment, I guess. This is not really like this.
Where did it come from?
Some people made it.
Who made it?
For who?
Dorset. He used to teach calculus before me, and pre-calculus. And then he left, and when he was cleaning his room out, he left me the pie hat because he really didn't want to take it with him.
What did you teach here before you taught whatever this is?
Algebra 2 and geometry and algebra 1.
Do you still teach geometry?
No.
Did you when we were freshmen or something?
Nope. I only taught geometry.
No, you did.
I only taught geometry my first year here.
And you taught.
I taught a lot of algebra 2.
I remember I used to come in here and ask you questions in the mornings before school. Whenever I had Mr. McClure.
But it says to Mr. Dorset, 3/14/2008.
from Mrs. Weber, who used to be the art teacher, Tiffany Feist, Megan Chris, Emily Rohr, and Allie Hayden. They made it in art class for Mr. 2007 was my first Pi Day here. Nope.
Sing and dance.
No, I had a CD of Pi songs that I played, but I don't think I sang. Then 2008 I rapped a song, sort of.
That's a math.
No, that was Lose Yourself in the Digits.
Oh my.
That's to Eminem's song Lose Yourself. But it's a really long song and I didn't memorize it all.
Okay, the math baby was really long and you remembered all of that.
I know. But I wrote Math Baby and Lose Yourself in the Digits I just stole, and so I think that helped me remember it because I actually wrote the words to it. But anyway, this Pi hat's just been in my closet and I decided to put it on that list.
Can you move all this stuff about there?
It's really heavy, I don't think I can.
What did well, one time we had the guys move Elvis behind his friend's desk and then she got really scared and like fell down.
She just fell on her butt. It was really.
And she like
She was
screamed
mad.
too.
She just got on the
I would have yelled at you also.
What did Parker say?
He said, well, yesterday he said, why is that guy in here? And I said, I don't know. And I said, it's kind of creepy. And he got really close to it and he said, his eyes are really creepy. But he really liked the hat on him today.
Did you find out exactly why?
Just AP. He said he's making the tour of AP teachers. So everyone yesterday was like, what did you do? Because apparently all of you think that Elvis is just for bad things, which sometimes
Well, he's for good things like the best police department.
sometimes he gets sent to people for silly things.
Like how criminals supposedly
Like
spent $200.
Oh no, yeah.
But like I feel like it's turned into rewarding teachers, and nobody wants this in their room. So
They came from Roseville from the
it's
cafeteria.
creepy.
Mrs. Scott's mom thinks she's gonna have her baby on my birthday.
Which is,
December 22nd.
she's not gonna last that long.
She's not even due till January.
I know, but she went to the doctor yesterday, and she's measuring 37 weeks, and she's 32 weeks.
And
Said
she
she
was
was
like, I guess he's just giant.
Mm.
But and I was like, it's twins. And she was like, if there's twins, you're moving.
She had her daughter a month early.
Yeah, she's going to have that kid soon.
On my birthday. His birthday. No.
She's gonna have a.
I know. That's why today, whenever she said she was talking about the baby and January at the same time, and I was like, "When are you due?" Or December, and she said in January, and I was like, "What did this pregnancy last? Like 3 weeks?"
She's been pregnant all summer. That's what's nice about it. So she started ahead of the game. The second derivative test, we're gonna use it today, and we use it sometimes. But honestly, it does the same thing that the first derivative test does. Sometimes the second derivative test is a quicker way to find max and mins. Other times it's just a pain if the second derivative is hard to find. But I'm gonna show it to you today because it's worth looking at. But it says let f be a function such that the derivative at c equals 0. So notice that means that c is a critical point. Right? That's what this means. And the second derivative exists on an open interval. So if you find your critical points and then you look and see what happens in the second derivative, then you can tell if it's a max or min without having to make the number line. And so we'll do one and I'll show you how it's really easy, and then we'll look at one maybe that the second derivative test would be terrible. So if we plugged in our critical point into the second derivative and we got a positive number, greater than 0 means concave up, right? So think about this is your critical point. If it's concave up, it's going to look like this. So we can say that we know that if you plug your critical point in the second derivative, then you know you have a relative minimum without having to check on either side of it. Well, we're still going to do that, but at times. So if we plug our critical number into the second derivative and it's less than 0, think about what that means, concave down. That's why it's always a relative max. And sometimes if you plug it into the second derivative and you get 0, that doesn't tell you anything. So you still have to go back and do the first derivative test, which is why most people end up saying second derivative test is dumb and I don't want to do it, because then I have to go back and do the first derivative test anyway sometimes. Why else would you not want to do the second derivative test? If your second derivative is awful, like lots of chain rule, quotient rule, don't waste your time doing the second derivative, just do the first derivative test and that will work. Here's the big thing. This is opposite of what you think, right? Greater than 0 is a minimum and less than 0 is a maximum. So always think about concavity when you're doing that. So let's look at one and see if we can make any sense of it. I feel like
You
I'm...
don't have any worksheets before the class?
We are.
That's good. Everything is just jumbled in.
I have a 4.1 to 4.3 wrap up also, like summarizing everything you need to know.
Like notes or a worksheet.
Like just like reviewing, like this is the stuff. We have extreme value theorem, we have mean value theorem, we have the first derivative test, we have the second derivative test, we have critical points, we have concavity, we have inflection points, right?
You say it like that.
So find all relative extrema. You don't necessarily have to do the second derivative test, but I want to on this one just to show you how it works. So relative extrema, step 1, find my derivative. And find my critical points, right? Because if I'm finding max and mins, I need to find my critical points. And how do I do that again? Set that equal to 0. We could make our number line, see what's happening on either side. But because this second derivative is really simple, second derivative test is not a bad way to go. So if you're going to do the second derivative test, step 1, well, after you do this, is to find your second derivative. And my second derivative here would just be 6x. Second derivative test says take your critical points, plug them into your second derivative, and look to see whether you get a positive or a negative number. And as long as you get a positive or a negative number, you'll know whether it's a max or a min. So if I plug in negative 2, 6 times negative 2, do you agree that that's going to equal a negative number? Which means it's concave down, which means I know that x equals negative 2 is a relative maximum. Is that any simpler than doing the number line? I don't know. The idea is it's supposed to be a quicker way to do it as long as your second derivative is simple to do. If I plug 2 in there, 6 times 2 is definitely a positive number. That means at 2 it would be concave up. And so I know that x equals 2 is a relative minimum. Notice I didn't actually write 12 and negative 12. I like not writing the answer because I feel like if you write 12, people want to say 12 is the number that goes with this, right? Like they want to say the maximum is at negative 2, negative 12. But that's not the y value, right? How would we find the y value that goes with this? You got to go all the way back to the original function to find the y values that go with these. And you could do that, right? Do you want me to do that?
We have to do that.
Yes. We talked about this yesterday.
I know, I just forgot.
Negative 8 plus 24 minus 5. 11, is that right? Yes. So this would be at negative 2, 11. And that one would be at 8 minus 24 minus 5. Negative 21. I think negative 20. Yes. On your test and on the AP test, they don't ever say you must do the first derivative test. You must do the second derivative test. You just have to know how to find max and min, whether you use the first or the second. I tend to use the first derivative test a lot more, just because sometimes the second derivative is a big giant mess. But I'll try to use it a little bit more as we do these. Let's look at another one. I think this might be my last example of the day. Oh no, just kidding. One more. Then that's not sure. Well, we'll see how much time we have left after this, I guess. AP just 1 times e to the negative x plus x times, what's the derivative of e to the negative x? E to the negative x times negative 1, so I'm just going to change that to minus there. Are you okay with that? Remember, use like chain rule, or e to the u times u prime. If I'm setting this equal to 0 and I have an e in that problem, I'm always going to try to factor that out if I can. So I could factor out an e to the negative x, and I'd be left with 1 minus x. Is e to the negative x ever going to equal 0? So I just have to solve 1 minus x. So I get a critical point of 1. You could make an underline from here. But we could also do the second derivative test. So let's do the derivative again. So what do you want to do? You want to do the derivative of this part, or you want to do the derivative of the factor part? We can. I'm going to show you though, it's really not that bad. But yes. Even though e is not just a number, e is a number actually. The derivative of e is really easy. So if I do the derivative of this, Rachel said she wants to use this one. What's the derivative of e to the negative x? Times 1 minus x plus e to the negative x. What's the derivative of 1 minus x? So is that just going to be minus e to the negative x? Could I factor out e to the negative x again? I don't know. Should I factor out a negative? Should I factor out a negative e or leave the negative? Because these both are negative e. So if I factor out a negative e to the negative x, I would be left with 1 minus x plus 1. Oh, on this one? But I took this times the derivative of this. So that would be plus e to the negative x times the derivative of that, which is negative 1. So that's where my negative came from. But what about the front? Why is the front one negative?
Shouldn't there be a negative x in this? Because it's, if you take out negative e,
If I take out negative e to the negative x from this part, that's just gone and I'm just left with that. Okay. So is that just 2 minus x? So now we can plug 1 in there and see what happens. And I would get negative e to the negative 1 times 2 minus 1. So just 1. Negative e to the negative 1. Is that positive number or a negative number without using your calculator? Do you know? That would be the same as negative 1 over e, right? It'd be negative. E is like 2.71. And if you put in the bottom the negative, that's going to be a negative number, which means that that is concave down. So I know that there's a relative max at 1 something. Not negative 1 over e, right? I have to plug that 1 back up there. Which gives me e to the negative 1, or 1 over e. Is doing a number line any faster than that? I don't know. Maybe. It depends. Either way, you gotta plug something with e. But not impossible. I would say on the homework today, if it says to use a second derivative test, I really want to encourage you to do it today just to practice it. But on the test, I won't require that you have to do the second derivative test. Okay? What if I gave you things like this? function, these are original functions, f of x. It says, give the signs of the first and the second derivative. And this is kind of the connection that we want to start making before we have a test. If you see a graph, you should be able to tell me what you know about the first and the second derivative by just looking at that. Because the first derivative has to do with increasing and decreasing. The second derivative has to do with concavity. So you should be able to tell me what you know about those derivatives by just looking at these functions. And that's what on Monday we're going to kind of wrap up and write all the connections that we should be making between these graphs. Now you don't have to write those perfectly. Notice I didn't even put any numbers on there. You just want to kind of get the shape there. So when they talk about the first derivative, your mind should be talking about increasing and decreasing because that's what we know about the first derivative. So looking at this graph, can you tell me? Is it increasing? Is it decreasing? Is it sum of both? Is it nothing? It's decreasing the whole time. So what do we know about the sign of the first derivative? It has to be negative. So I can say, I know just from looking at this graph that my first derivative is less than 0 because it's decreasing. When we see questions about the second derivative, we should be thinking about concavity. Concave up, concave down, is it concave at all? What about this one? Is it concave up, concave down, no concavity? Concave down, so what do we know about our second derivative when it's concave down? So we could say that the second derivative is less than 0 as well. There's no work to go with that, it's just knowing the relationship. So what about the first derivative on this one? This is an increasing function. So increasing means that my first derivative is positive, or I could say greater than 0. What about the second derivative on this one? Yeah, it kind of goes back to that piecewise one that we started with this morning. Your second derivative would equal 0 on this. Think about this is a linear function, so if you took the derivative once, it would be a constant. If you took the derivative again, it would be equal to 0. Or if it has no concavity, that means the second derivative has to equal 0. And so what we're trying to get to is be able to answer a lot of questions about graphs without really needing a function to even go with it. Okay, so I want you to finish the homework from yesterday. So let's figure out which assignment that was. 21 through 29 odd. So 21 through 29 odd. That's the rest of yesterday's. And then, let's see what else we got. You really can do almost all of this. I don't know. Let's say 33 through 37 odd. So that only takes away 3 problems. On Monday, I'm going to give you those rest of those 3 problems and then probably a worksheet to go with that. I think the assignment sheet said a worksheet somewhere. Did we say a worksheet for this section? I imagine things that might be the next time. It says worksheet. No worksheet. Okay. I might add worksheet. So 33 through 37 are the second derivative. 21 through 29, most of those are looking at the graph and saying where's it increasing, where's it decreasing. Pay attention whether it's the original graph or the first derivative. But not a whole lot of computing on those ones from the other.